Okay, so let's see how to create our own bootloader program. So before moving on, what is about bootloader? Let's see what is meant by this operating system. So operating system is a system program which manages the user processes uh, and give an interface to the users. After providing the interface, users can interact with the computer. Basically, operating system hides the internal complexity of the hardware from the user, then give the abstract interface, because in the user's perspective they have no idea about how this hardware works, because hardware is much complex for the user level. So I mean, the user is just a normal person. He can't, or he will be facing so many difficulties to deal with these hardwares because of the lack of the knowledge. But if we provide an interface to the users to deal with the hardware, then it will be much easier and much efficient for the users as well, and also will be user friendly. So that is the place where operating system invented. So basically, operating system give an abstract interface to the users, and users can deal with operating system, and operating system deal with the hardware. Okay, so basically operating system is like a overlay of this whole process, but it is necessary, otherwise users are unable to get their work done. And there are so many operating systems all over the world, but these are the very popular ones. So the Windows is well-known operating system, and Android is a mobile operating system basically, and Mac OS invented by Apple, and Ubuntu is one of the most popular well-known operating system, and it is open source operating system. What is meant by open source is, when you are considering Windows or Mac OS, they are only giving the ability to work on top of it, but you can't edit anything in the Windows code, or let's say Windows kernel. But when it comes to Ubuntu, since it is open source, you can edit the code, and you can even make your own operating system and publish it legally. Okay, you can legally edit this code, and you can even make your own operating system. And Android is actually one of the most popular distribution of this Ubuntu, because Android using GNU Linux environment, and we can consider this Android is a distribution of Ubuntu for mobile devices. Okay, so those are the operating system. So what is meant by bootloader? So bootloader is a code which runs before the operating system. Note that this will be running before the operating system, and maybe you can even consider this bootloader is the very first part of the operating system. That's all right. Or you can consider this bootloader is running before the operating system. Okay, basically it's a part of the operating system which runs first. So when you are turned on a computer, first what happen is it will run a post program. So post means basically power on self test. So it will be looking several stuff. Then after the post program, it will be running BIOS. So BIOS means basic input output system. So it will consider about your hardware devices and whether they are correctly work or not. Likewise. So after the booting BIOS process done, it will run the bootloader. Okay, so bootloader runs the operating system, because as I said before, bootloader is the very first part of the operating system. Then after running bootloader, it will run the operating system, the whole operating system. Then operating system will take control of the computer or your PC. Then users can deal with this operating system and get their work done. So this is the very basic boot up process. So there are much details, but this is the very abstract view of the boot up process. And yeah, this process is known as booting, and bootloader can be considered as the very first part of the operating system. So if we consider more detail about bootloader, so bootloader is able to read the very first 512 bytes of the memory or the hard disk. So until it reaches its signature value. Okay, so now if you don't know much about operating system, you might be thinking, what is this very first 15 byte, what is this magic number, things like that. Okay, so let me quickly explain this. So imagine this is your hard disk, okay, hard disk or any other storage device where your operating system exists. Okay, so this is the device where your operating system is stored. So imagine your hard is maybe, let's say, 1 terabyte, and assume your OS has been taken, let's say, I don't know, maybe 5 GB. Okay, so assume this is your hard disk, HDD, hard disk drive, and there are some sectors. Okay, so sectors means nothing but there are memory locations. Okay, so there are so many details, but I'm not going to much details. I'm just giving you the idea. So imagine our operating system is existing such a place. Okay, my drawing is bad, sorry about that. So let's say this is 5 GB space of the hard disk, and this is the, let's assume this is the part where bootloader exists. Bootloader exists in this part, and it is around, it is not around, but it is exactly 512 bytes. Okay, so this 512 bytes is the very first part of the operating system, and rest of it contains other utilities and stuff like that. Then after when it happening to the boot up process, first this code will be run like this, and after the execution there will be a some number called magic number. So I'll name it as mn, or it is known also known as signature. So this signature implies something like this. Okay, so after this code run or bootloader run, the operating system will be copied to the RAM. So let's say this is our RAM, and now operating system is loaded like this. Okay, then operating system will run, and it will take the control of the computer, and it will give the interfaces and services and all of that. So this is basically boot up process. So what you have to understand is this signature, what is meant by this signature. So signature is basically a kind of a sign which indicates the end of the bootloader, because when your processor read instruction by instruction, when it reaches to this signature, it will know that this is the end of the bootloader, and afterwards it should be run the operating system. Okay, so that is why it is known as booting process, because this operating system is run by itself. So that is the place where the word booting has come. Sorry, booting came. The word booting came, uh, which means it lift off itself. Okay, after this bootloader runs, it will automatically run this operating system, and it will load it to the RAM. Then afterwards, it will take the control. Okay, so anyway, this is the very basic introduction about boot up process. So let's move further. So how to create our own bootloader? So bootloader is a code which runs before the operating system, as I said before. By version it runs here. Okay, I think I explained all of this. So let's. Okay, so this is the what I said before, the magic number. So magic number is a value indicate the end of the boot code. So there are two types of magic numbers. The first one is 0xA55. It is not. It is a little endian. This is just a name, and 0x55AA as big endians. Okay. So these are just processor architectures. So these are differ from processor architectures. Like when you are considering Intel x86 processor architecture, it contains or it follows little endians. Right. Then if you consider about AMD, as I remembered, I'm not sure, but as I remembered, AMD follows these big endians. So likewise, different processors follow different magic numbers. It doesn't matter. That is the way how it works. So since we are considering about this Intel x86 specific architecture, just remember we are using little endians. Okay, so if we want to move another processor architecture, then we have to choose one of these. But in this case, we are only going to focus about this little endian architecture. Okay, so this is this so-called magic number depends on the processor architecture, as I said before. It specifies which one is the MSB. So MSB means most significant byte, and which one is the LSB. So LSB means least significant byte. Okay, so this is just a representation about how these big endians and little endians works. So when you are considering about a whole byte, okay, a whole byte, this can be divided as two parts. So first one is, let's say, MSB, most significant bit. The second one is least significant bit. So if we write like this, or if we consider like this, then this meant as big endian. And if we consider our byte as two parts, and the first part is LSB and the second part is MSB, then it follows little endian structure, okay, or little endian definition. So just remember about that. So this 0x AA55 and 0x55AA, so these are hex numbers or hexadecimal numbers. Okay, so since they are hexadecimal, this contains 16 bits. Okay, so if we divide it into two parts, so if we divided, sorry, so if we divide it into two parts, one part will be 8-bit, another part will be 8-bit. So this is the first byte, because 1 byte equals to 8 bits, and this is the second byte. Okay, so if we consider first byte as MSB, then it is big endian. If we consider second byte as MSB, or most significant byte, then it is little endian. Okay, this is just a architecture, how these processors and other hardware stuffs work. Okay, so this is about magic numbers. Okay, so now we can do some coding. So before going on to coding, I will explain about our environment. So we are not going to do any C++ or Python or some code like that, so some regular coding like that. We are going to do assembly. We are going to use assembly language. So this is the place where things getting hard. Okay, this is kind of complex. Okay, I'm not saying it is completely complex, but it is complex than our regular programming languages like C++, Python are much easier than this assembly. Okay, so when it comes to assembly, we have to focus about how this hardware works and things like that. Okay, so make sure uh, this is not about uh, a general programming. Okay, general programming means we are not going to use C++, C or Python or Java or something like that. We are going to use assembly language. Okay, so those are the languages based to C and C++ and things like that. Okay, so these are kind of old languages, but in this case we are going to use this. So we are going to use create a bootloader in GNU Linux environment. So that's why I said before, GNU Linux is open source. Since it is open source, we can do, or we can make our own source files and things like that. But when it comes to Windows environment, we can the same thing, but it is kind of hard. Uh, Therefore, we are going to use GNU Linux environment. Okay. So in here, we are going to create a very basic x86 specific bootloader which prints the hello world. So if you are a Windows user, uh, operating system is very complex thing. But since we are going to focus about very basic stuff, we are just going to print hello world. Okay, so it is very basic, but there are so many things we have to learn. So first you should have Ubuntu installed on your computer, and it is not necessary to install as your main operating system on your computer, but you can use this virtual box. So if you don't know about what is this virtual box mean, uh, this is the virtual box. So if you don't have virtual box installed on your computer, you can simply go to the Google and download from over here. Okay, so I'll put you the links, and after you installing VirtualBox, you can install your Ubuntu iOS like this. So if you don't have Ubuntu iOS, then you can simply go over Google and search for it, and there will be so many distributions. You can simply download your iOS over here. So I'm not going to explain how you're downloading these and installing and stuff like that. You can do those by yourself, because those are very easy tasks. So after you're installing your operating system or your Ubuntu as a virtual machine, you can just simply double click and open it up. So this will take some kind of a time, so I'm not going to waste it. So let's move on to the our slides again. Okay, so now we have Ubuntu. Then we need this GNU Assembler. Okay, because we are going to use assembly language. Therefore, we have to use GNU Assembler to compilation processes. So you will be need this, and I will show you how to install this stuff as well. Then afterwards, we have to run our bootloader. So in order to run our bootloader, we use this qemu-utils. Okay. So let's take a look out how we install GNU Assembler and stuff like that. Okay, so these are the stuffs I said before. First you have to download VirtualBox, then install VirtualBox, then we have to install GNU Assembler. So I hope now our VirtualBox has been booted. Okay, so this is my Linux environment, my Linux virtual machine environment, and you can make your own environment as well. So this will take some time to load. Okay, so let's move on to the sites again. So after you're installing Ubuntu on your computer, you have to use terminal to install the packages, relevant packages. So if you want to install GNU Assembler, you have to type sudo apt install binutils. Then if you want to install a QEmulator, you have to type this command. So I'm not going to install those because I have already installed, but I put these things on the description, then you can install those packages as well. Okay, so I will show you how to type your commands. So you have to go over your terminal like this, then you can simply type sudo apt install binutils. Then it will ask for the permissions. You just simply type your password, then afterward it will asking whether you have to install or not, like that. But I'm not giving that message because I already installed it. Okay, and after you installing this binutils or GNU Assembler, you have to install this qEmulator. So you have to type this code sudo apt install qemu-utils, so on. You have to type this, then you will be having this type of a icon to indicate you have successfully installed your virtual machine. So since I'm already installed it, I'm not going to install it again. So you can type that code and install it very easily. Okay, I think that is our environment. Okay, so now we have to move our code, but before moving code, I will explain what we are going to create. So first, the very first thing what we have to create is to create our boot source file. So this is the file where our code is going to implement it. Okay, so if you are familiar with other programming languages, when we are dealing with C++, we make a source file as .cpp. When we are making Python file, then .py. When we are making C file, then .c. So likewise, when we are working with assembly, we are creating this boot.s as a source file. Okay, so we need to create 15-byte binary file that contains 0x55a at the end. Okay, so I will explain how you are going to specific this signature, how you specific this size of binary file, and how you going to create binary file and things like that. So, in the in following slides. Okay, but now we are going to deal with 16-bit compatibility because modern operating systems deal with 60-bit or 64-bit or 32-bit process architecture, but these are kind of complex. Okay, so as a introduction to the bootloaders, we are not going to focus about these so-called 32-bit or 64-bit process architectures. Instead of that, we are going to focus about similar process architecture, but it is kind of easy. It is not complex than these 32-bit or 64-bit. It is just a 16-bit. Okay, so we can easily deal with that. Okay, so and also since this is happening in boot level, this bootloader should run at ring level 0. Okay, so now I will quickly explain what is this ring level mean. Okay, so there could be having a couple of ring levels on your computer. So let's say your computer will be having 0, 1, 2, 3 as ring levels. So these are just privilege levels, which means 0 is the highest privilege level and 3 is the lowest privilege level. So assume you are in highest privilege level, then you can do anything. Even you can control the hardware by yourself. Okay, but it is kind of dangerous because if you done some mistake, then it will cause maybe a physical damage or something like that. But this is the highest privilege level, and the ring level 0 is the lowest privilege level, and normally this is the place where users exist, because users are normally make mistakes. So those mistakes could be handled by the operating system instead of just directly forwarding to the hardware. So that's why users will be having low privilege level because of their own sake. Otherwise uh, they will occur some hardware failures or something like that. So just remember, operating system is in this highest privilege level. So this operating system mean normally bootloader is at this ring level 0. Then there will be a process called initial process or or init process or startup process or something like that. So this will be the very first user process run by the operating system, and this will be in ring level 1. So it is kind of having low privilege level than ring level 0. Then there will be some services at ring level 2 as well, services or processes. Then user will be at ring level 0, and user can run applications at ring level 0. So that's why we are going to focus about this bootloader. So bootloader means basically using this ring level 0. Therefore we need to be very careful when we are deal with this stuff. That's why we created a virtual machine as well. Okay. Okay, so let's move on to the code. So first I will clear this terminal. Okay, so this is the my previous one, so I'll just move it over here and I'll create a new folder in the desktop. So if you are familiar with GNU commands, you know how to create uh, a, a new folder. But if you are not familiar, then you can simply right click and create a new folder like this. Okay, so I will name it as, let's say, bootloader 2, because I am already having this bootloader 1 file over here. You can name it as anything. So now since I have been created this new file, I can move to that file. So cd, so ls, then cd desktop. So now I'm in the desktop folder. So if I listed it, it will show this bootloader 1 and bootloader 2. Now I'm going to move that bootloader 2 file. So cd bootloader 2. So now I'm in bootloader 2 file and it is empty at the beginning. So now I have to create a file called boot.s. So in order to do that, I use this touch command. So touch boot.s. So this will basically create this boot.s source file, and you can also open this folder as well. Then you will be seeing this boot.s file. Okay, so after creating this file, we can open this. So if you are already familiar with GNU Linux environment, you can simply use vim to open your file and do your codings. But if you are not familiar, you can simply right click and open within a text editor. Okay, so now we have to do some code. So let me can we size the size okay. So first thing we have to specify what is the processor architecture, or what is the bit we are going to use. So we are going to use a 16-bit processor architecture. So you have to specify it like this: dot code 60. Okay, so let me make a comment as well. So okay, I'm not going to make a comment, I'll just explain it right away. Then I have to initialize our very first user process. So in this case, I will name it as global init. Okay, so this init can be any name. So if you like, let's say start process, you can name it as well. But in this case, I'm just using init. And normally when it comes to operating system, they are using init as the default name of the very first user process. And after initializing that process, you can call that that as a function. But note that when it comes to assembly languages, since it is a function, it will consider as a variable. It is considered as a memory address. Okay, so that's why I specified it as like this. So init, then I can write anything over here, but for explanation purposes, I just implement this code. So basically it will jump to init, but it will do nothing. Okay, and yeah, this is the very first code you have to type as your boot.s content. Then we can move further. So before going to move further, I'll show you how to compile this as well. Okay, so since we have created the bootloader as a source file, we need to compile this to make it as an object code. So in order to create our boot source file as a boot.o file or object code, we are going to use this command as or boot.o boot.s. So basically this boot.o means our object code name, and boot.s mean our source code name. And this is the place where GNU assembly comes handy, because since we need to compile this boot source code as a boot object code, we need to use this GNU assembler compiler, GNU assembler. Okay, it's not a compiler, it's way beyond, the compiler is way beyond assembler, but okay, you can even consider it as a compiler. Okay, so let's compile our boot source code as well. So I'll clear our previous code and I will list our content. So we are only having boot.s source file, and if I write command like this, boot.o, boot.s, now you can see two files over here. So this is our object file, and if I list it like this, so now we having two files, but let's see what are the sizes our files got. So you can write ls minus lh. So this L mean list and H mean human readable. So this is kind of like a pipe, a very simple pipe, to get a detailed list. So these are the file sizes. So as you can see, our boot.o file is having 696 bytes and our source file is just 38 bytes. But as I said before, we need a file which only contains 512 bytes. But now as you can see, it has been exceeded it already. And this is the place we need to do some stuffs again. So as I showed, after compiling, this will create a file which is larger than 512 bytes. So therefore, in order to reduce the unwanted additional stuffs in this object code, we can make that object code as a binary file or .bin file, and it will reduce the file size as well, and it will only contain the essential stuffs. So it will remove our other additional stuffs. So this is the place we can use GNU Linker. Okay, so Linker is kind of like a service that GNU has been given to us. By using GNU Linker, we can create our own binary file to our object code. Okay, so this is the command for that. So ld means basically we are going to use linker, then boot.bin mean our binary file, then oformat mean it's oformat binary mean it's just creating a plain binary file. Then this is the entry point. Init means we are labeling our binary code's entry point as init, because that's how bootloaders works. Then boot.o means our relevant object code that we are going to convert as a binary file. So give me second. Okay. Okay, so let's see how to create this so-called bin file as well. Okay, so let me clear all of this. So first I will just listed our current file sizes. Then I will call my linker. So ld o boot.bin, then o format binary, our entry point as init, then boot.o as our object file. Then press enter, so it will create a binary file. So now let's see what are the sizes. Okay, so as you can see, now it's only 2 bytes, so our size is greatly reduced. Okay, so this is the place where uh, the things getting kind of complicated, because now we have created source file, object file, and as well as a binary file. But the binary file is uh, highly size reduced file, and it is now only 2 bytes, but as I said before, we need a file contains the size of 512 bytes, right? So let's move our slides again. So this is the thing that I said before. Then it's a create a boot.bin file which contains only the essential stuff. So now it's roughly like 2 bytes, so as I shown before, but we need a file which having 512 bytes. And not that we are not going to exactly create 512 byte, but we are going to create 510 byte file, because at the end we have to specify this magic number as well. Okay, so now you already know this magic number is 2 byte. Then the total will be 510 plus 2 bytes will be 512 byte, right? So let's fill our binary file until it become 510 byte file. So how we are going to do that? Basically, let me move on to our object code again. So this is our object code. Now we need to specify our size as well. So in order to do that, I will type dot fill, then 510 is our size. But if we type only like this and compile it, it will create the file, but when we are adding much more instruction or more instruction for this code, then our size will be enhanced. But in order to avoid that, we need to specify every time we are going to insert instructions, it should be reduced from this size. So minus dot init, which means from init onwards it should reduce size. Then other can be contains just plain ones and zeros. So this will successfully create a file which contains only 510 bytes. And note that even if you are adding new instruction for this or for like this, but it won't increment the size. It will only contain 510 bytes. So let me save this and let's move our terminal again. Then let's compile our object code again. So you can simply use up arrow to go the previous commands. So I compiled our source code again, then our binary file again compile, then let's ls minus lh. Okay, so now as you can see, our binary file only contains 510 bytes. So before it was 2 bytes, but now it's 510 bytes. Okay, so far we are good, I think. Okay, now this is the place we are going to specify the magic number. So I'm not going to go much detail about this magic number because I explained it before. Okay, so remember, we are going to specify our magic number as 0xAA55 because we know that we are going to use Intel specific architecture. So Intel, they use little endians like this. So when we are using little endians, since we need to specify our magic number as 0x55AA, we need to specify in the assembly it as 0xAA55. So it is kind of tricky, but you will get used to it, because we know that in little endians they are consider the last byte as MSB and the first byte as LSB. So if you specify your last byte as 55 and your first byte as AA, then it will read like this, 55AA, because MSB always comes first and LSB always comes first. So it will give what we exactly wanted. Okay, so this is the signature. Wait, let me show you. So this is the signature what we want, and this is the signature what we are going to type, but it automatically swap the values like this and give our magic number or our signature. Okay, so let's again move on to the our Ubuntu virtual machine. Now I'm going to enter our magic number. So you have to use .word 0xAA55. So remember, you are specifying it as simple. Okay, do not type AA55, because when it comes to hexadecimal, this A means another value, when this AA means another value. Okay, so those are two different values. Therefore it is better you use your signature like this and save it. And let's compile our source code again, as well as our object file. Then let's see our size. Okay, so now it's only 512 bytes, which is exactly what we wanted. So before it was 2 byte, then we make it as 510 bytes. Now it is 512 bytes. Okay, so now the size of bootloader is completely initialized successfully. Now we can move further. Okay, so now our boot.bin file is exactly 520 bytes. Now we can run this bin file or binary file. So this is the place where you need this qemu-utils. So as I said before, you have to install first Ubuntu, then GNU Assembler, then qemu-utils. Okay, so Ubuntu we already used, GNU Assembler we already used. Now we are going to use this qemu-utils. Okay, so qemu-utils basically runs our binary file. Okay, because we don't have a specific machine to run our bootloader, therefore we need to get used to a virtual machine. So this is the place where a qemu-utils comes. And when you want to run your binary file, you have to type this command, qemu system x86 64 and your bin file name boot.bin. But remember, this will show nothing because we haven't implemented any specific code for it, and it will only run a single iteration as well. So it will just probably it will give some error, or maybe it will give a blank interface, but it doesn't matter. We are going to implement more code later on. So let's call our qEmulator. So I'll clear the content and let's call our qEmulator qemu system x86 underscore 64 boot.bin. Press enter. So if you install your qEmulator successfully, this even give this message, but it doesn't matter. If it is pop up this window, which means we all okay. So as I said before, it doesn't give a blank sign because we haven't implemented any, but it works. Okay, so I'll close this and clear the content. So let's move further. Okay, so as you said, as you seen before, it runs only a single iteration. So let's make it as a complete loop. Okay, so loop means basically this is a single iteration. So when it comes to loop, it will run again and again and again. But we are not going to exactly rebooting. We are not going to reboot our qemu-utils virtual machine, but we are going to re-execute our binary code or our bootloader. So this is the place we need to call, or we need to use reset vector. So reset vector is some kind of a specific place where we can call our functions again and again. Okay, so when it comes to assembly, we need, yeah, we use this piece of line to specify that. Okay, so these are just hexadecimal numbers. So this is indicate the largest memory address that we can visit, and this indicate the lowest memory address that we can visit. And remember, when we are specifying some value as dollar sign, it will indicate this is exactly a value. Okay, this is exactly a hexadecimal value. That is how assembly works. And yeah, so this is just a name. So this process is known as warm reboot, because we are not going to uh, actually rebooting. We are just re-executing our uh, binary file. So I'll remove this jump and specify it as ljmpw $0x f and dollar sign 0. You don't need to specify it as like this, because it already indicate the 0 like this. Then save it, compile it, and boot.o file as well. And now we can run our binary file. So as you can see, now there is a small blink. I don't know, maybe you can see it. This normal blink gives, when you are calling this uh, jump to reset vector function, or jump to reset vector instruction. Okay, so this is our loop, and we need this loop as well. So I'll just close this up. Let's move on. Okay, so now we are going to more deep, and now we are going to focus much complex stuffs as well. So now we are going to basically print a character. Okay, so since we are dealing with assembly, we can't use this printf function, because assembly do not provide any functions like this. But if you are familiar with C or C++, then they will give printf. But now we are going to see what happened inside the printf. This is the place where assembly comes. Okay, so it is kind of complex, but you can get used to it. Okay, so now we are going to focus about hardware services. Okay, so when it comes to hardware, we use interrupt to deal with such things. So remember, every process, every thing you done within OS is an interrupt. Even if you are press a key, it is an interrupt. Even if you are open a tab, it is an interrupt. Even if you are, let's say, reduce your volume of your, I don't know, maybe media player or something like that, it is even an interrupt. Okay, so everything related to operating system and operating system user processes are interrupts. So now we are going to manually call this interrupt in order to display such things, some things. Okay, so according to Ralph Brown's interrupt list, he specified the video interrupt as 0x10. So this video interrupt basically mean to print some value. And remember, when we are calling interrupt, this interrupt only deals with specific registers. So we can't use another registers. Remember, this video interrupt will deals with AL register. So AL means basically like a variable where it stores what we need to print. So this interrupt only works within this register. And when we are dealing with the machine structures, we can't use A, but we can use this value to indicate A. But I will show you how do we even specify the exact values as well. Then we need to do some piece of code as well. But for now, just remember we are indicating A as 0x0e41. This is basically mean ASCII A. Okay, so ASCII means a universal structure. Yeah, specified a lot of characters. Okay, so A is one of them, and A is identified as this hexadecimal value. So what we are going to basically do is we are storing this value in AX register or AX variable. But as I said before, when we are calling interrupt, it will only print the things which are in AL variable. But since we store our A in AX, it will automatically pointed to AL as well. Okay, so even if we store A in AX register, when we are calling interrupt, it will print A. Okay, so it is kind of complex, but I'll not going to focus about registers further because it is another topic. Okay, so let's go our code again. Now, as I said before, first we have to initialize our AX variable as 0x0e41. Therefore, we use this command, mov command. So we are setting our AX register as 0x0e41 like this. Then we are going to call interrupt. So the assembly instruction is int, and which int, which means what is the interrupt what we are going to call is 0x10 interrupt. So there are so many interrupts. This is the special interrupt in order to print something to the display. And after the code executing, we are going to end our program, which means halt. Okay, but remember, when you are specifying halt, it doesn't mean your code exactly end over here. Okay, because it need to consider these lines as well. It will consider those. Then let's save this and let's go to the terminal. Okay, what is this? Okay, so that is the thing I have been missed. So when you are calling an interrupt, you should specify it as a value, because we are going to call this specific interrupt. Okay, so it should be uh, considered as a value. So that is why I put $sign. So let's compile our stuffs again and run it. Okay, so as you can see now, it successfully printing our letter boot A. Let's go back to presentation. Okay, so it will print A on the screen, and as I said before, you should compile your boot code and binary file again and again before calling qEmulator. Otherwise, uh, it won't work. Okay, so now we are going to print a whole text. Okay, so this is kind of difficult again. So in order to print a hello world as a whole text, since it is a whole text, we are going to split it as characters wise, and we are going to print this character by character. So what it means, so let's say hello world is our text, then H means one character, E means another character, and this L means another character. Likewise, it will go until it reaches to the end. So we need we store our word, then we get the address of the first byte of the text, because this word is a byte. Okay, because as I shown you before, this is ASCII character, and it returns and it indicates, actually it indicates 2 byte, but when we are deal with the instruction, you will see it returns this byte address, which means let's say a pointer to this specific character address. Then we are going to grab the value which contains this address. Basically it is H. Then we calling interrupt, so it will print the word. So basically if we run this algorithm in single iteration, it will just basically print only first character, which means H. And if we want to print the whole text, we need to make it as a loop. So let's move to the code again. Okay, so I need to do some changes. So first I have to specify I'm going to use as key structure. So 0x0e41, and I'll store it in AX register. Now I'll make another instruction like this, and this hold our hello world text, hello world as a text. What we need to specify is using ASCII. So dot ASCII, but it is better if we use ASCII, because when we are run this as a loop, if we use ASCII, this automatically point to its next byte in each iteration. So in the first iteration it points to H, then the second iteration it points to E, then the third L. Likewise, it will go up until to the end of this text. Then we need another register to store the address of the first letter of this text. So I'm going to specify it as well. So I'm taking the address value of message and save it in bx register. So now this bx contain the address of the very first byte of this text. And now since we having the address, then we can grab the value from this address and store it to our AL register. Then when we are calling interrupt, it will print the content of AL, which means basically the first letter of this message. So again I'll call move. So since I'm using pointers to get the value, I should specify it as a bracket. So the assembler know I'm going to call the value which is pointed by this memory address. So bx. So this contains the memory address of h. Now the value should move to AL. So remember, since I'm calling this as a first byte, actually this is size of 2 bytes, okay? Because ASCII value contains 16 bit, therefore it is 2 bytes. But remember, when I'm calling this as the very first byte, it indicates 2 byte as well. But it will give as a single memory address value. Okay. Now we can call our interrupt 0x10 and halt. So this will work correctly, but this will give some error because before I just only print a single value, now I'm going to print a whole text. So when we are trying to print a bulk text like this contains more. This will take more space in the memory. So normally one text will take 2 bytes, but since this character having maybe 1 2 3 4 5 6 7 8 9 10 11 12 13 characters, it will take 26 byte. So we need to tell our linker, now we are going to use a whole text, therefore we need to specify it as well. So let me show you what I'm telling you guys. So I'll make it a terminal. Let's compile. So since we are compiling boot source code as object code, it will compile well, but now we are compiling it as a binary file, it will give some error, okay, because the appending won't work correctly. Therefore we need to tell our linker like this: boot.bin or format binary. So this is our entry point, and now we are going to use a whole text. So use this registry value, or use this amount of a value to our text in boot.bin, boot.o. Then press enter. Maybe I have done some mistake. Okay, it is not ls, it is ld. Okay, this is not ls, ld. Okay, now it compiled well. So let's call our QEmulator again. Okay, now it prints h. So this is just a one character at a time, because we ran only single iteration. So let me close this and move on to the presentation again. Okay, so this is the thing what I have been explained so on. This will only print a single character at a time because we run only one iteration, and since we are using 16-bit address space, it is not enough to represent the entire text. So we need to tell our linker manually that we are going to use a much larger space as our starting memory. So this is how we specify it. Okay, and yeah, it printed H, but now we need to print the whole text. So it is basically we are creating a loop, then it will print character one by one, then we will be having a whole text. So in order to deal with registers, or in order to deal with a loop, we need to specify special registers for this purpose. Okay, because in this case I'm going to use a special function called, or special instruction called load sb. Okay, so this load sb only deals with these two registers. Therefore we are going to use these two registers and ax as our initial value. Okay, okay, let's move on to code again. So I'll remove maybe, okay, I'll remove all of these and I'll specify our initial value 0x0e41 and store it in ax variable. And as I did before, we are going to take the address of this first character and store it in si register. So msg si, then I can specify another function like this. So in this function we are going to load the value which is pointed from this address to al register, because the video interrupt print the content of al. So if we load the content of this si to al, then it will print the corresponding value. So load sb. Okay, so before assigning, okay, so we have already assigned, but as I said before, we are going to use a loop. So every loop should have a breaking point, otherwise it will make an infinite loop and our computer will be crashed. So in order to avoid that, we should specify a breaking point. So therefore we tell our code, if we reach the end of this text, then stop it. Okay, so the end of this text indicate by 0. Okay, so we compare is it equals to 0, which is the content of al, because in this si we grab the address of this first character, then we load this this address pointed value to al. Now we are going to compare this al as al with 0. So suppose now we are in the end of the text, then our al will be 0. So if it is 0, then our program should be end. If it is not, then our program should be continue. So if suppose this is equal to 0, which means we are now basically at the end of the text, so the program should be ended. And let me specify another function like let's say, I don't know, let's say end maybe. end means basically halt. So if it is 0, then je end. So this is a specific instruction to run the content of the end. And if it is not, basically we are calling our interrupted vector in order to print the content of AL register on 0, and we are going to make it as a loop. Therefore I'll jump print char memory address again. So when I'm specifying like this, it will simply jump over here, then do the process again. If it is equal to 0, then it jumps over here and end. If it is not equal to 0, then it goes here and jumps again. So likewise it happens until it reaches to the end of this text. Okay, I think we all done. So let's save this and let's compile our object, compile the source file again. Okay, okay, my bad again. When I'm comparing this value of AL, I should specify it as 0, right? Because if I specify it as like this, then it indicates the register value, and actually there is no register known as 0. So basically what I had to do is specify it as a value. So this is basically means 0. Okay, this dollar sign indicate a specific value, this percentage sign indicate a specific register. Right, so now let's compile again and again. Another same mistake again. So note that when I'm calling interrupt, it again should be a value, because we are going to call this specific values interrupt, basically a video interrupt. So I assume there is no errors. I don't know, maybe let's compile it again. Okay, we have completely get rid of the errors. Now I'm going to call this link ID. So note that I'm going to create this Ttext link ID. Okay, I'm not going to call the very first link ID, because since we are going to deal with a whole bulk test, we need to specify it as like this. Okay, now we can call our qemu-emulator. Okay, so this is how we print a text. So as you can see, now we printed this hello world text. Okay, so you can name it as any text. So I'll name it as my name. It doesn't matter how it longs, but maybe if you long a very long text, it will give some errors, because we are only going to create a file contain for 112 bytes. So maybe it will give some error, but I don't know. Let's try it as well. Okay, gladly it wasn't given any errors, but don't use a very large text to print. Then you need some other stuffs as well. You need to specify some other stuffs as well. So this is how a bootloader works, and we done about everything. So we successfully created a very basic bootloader, and maybe you can make your own operating system to study more by studying more deep stuffs as well, and maybe it will be a $1 million worth operating system in future. So this is the very basic step to create your own operating system. So now we successfully created the bootloader, and later on let's see other stuffs as well. But for now we successfully created a bootloader. So thank you.